Good evening. This is Donna Blomquist, librarian at the LaSalle Public Library. Welcome to tonight's virtual program, Winter Weather 101. Before we begin, just a few reminders. On Wednesday, January 11th, that's tomorrow evening at 7 p.m. Central Time, the library will join libraries across the state in virtually hosting best-selling essayist and poet Ross Gay, who will discuss his most recent collection of essays, Inciting Joy. Mr. Gay is the author of 4 books of poetry, winner of the PEN American Literary Gene Stein Award, and winner of the 2015 National Book Critics Circle Award, as well as the 2016 Kingsley Tufts Poetry Award. And on Tuesday, January 17th at 6 p.m. Central, the library will virtually welcome back Claire Evans with her newest presentation on the life of Alf White, an unassuming country veterinarian who practiced for 50 years in one of England's most beautiful places, the Yorkshire Dales. White rose to international fame later in life under the pen name James Herriot, as he recounted the heartwarming animal stories and colorful characters of a bygone era, inspiring a film and multiple television series. Of course, we are talking about All Creatures Great and Small. Bask in the visual beauty of Claire's recent visit to the Yorkshire Dales and learn the surprising story of a vet whose books still entertain millions in this unique presentation. And then on Tuesday, January 24th at 6 p.m. Central Time, the library will virtually host author and former photojournalist Kathleen Garrity when she shares how her book, thanks to her, Finding Power and Inspiration in Your Family Photos, came to be. In this unique program, Kathleen will tell the story that began with a humble garage sale and morphed into a multifaceted research project. More than a recap of American history from 1900 to the 1950s, thanks to her is a metaphorical snapshot of women's lives during those decades. As always, all library programming is free and open to the public. It is also shareable, so please feel free to pass the information on to others. We also want to hear from you tonight. Please post your questions for tonight's program in the chat. And now, tonight we welcome Nick Bartholomew from the Illinois Storm Chaser. Nick will help us understand just how Illinois winter weather works. Nick, are you there?
I am here.
Great. Okay, I'm turning it over to you.
Awesome. Well, welcome everybody. I'm going to share my screen so we can go ahead and get this presentation underway. All right, back to here. All right, are you able to see my screen?
Yes, we can. It's perfect. Thank you.
Awesome. So once again, welcome everybody. Thank you for tuning in tonight for this presentation about Winter Weather 101, the types of winter weather that we see locally, as well as what exactly causes our specific winter weather. So to start out, I'm going to go through a little bit of an introduction myself, as well as Illinois Storm Chasers, our parent company. Move into a little bit about local winter climatology, weather forecasting, the complexities of winter weather forecasting. As we all know, we deal a lot of times with some places posting some astronomical snowfall totals. So we'll explain why that happens and why that stuff gets out. Follow that with a little bit about wind chills, what it is, how it affects us, and the potential dangers of it. Going a little bit about model soundings, kind of when we look through the temperature profile through the atmosphere, how we can determine what the precipitation type is going to be. And then because we do have a system coming up on Thursday in our local area, I'm actually going to go through new model runs of the upcoming weather pattern, see what kind of weather specifically we're going to see around our area. And then we'll finish also with a Q&A. So again, my name is Nick Bartholomew. I'm owner and founder of SWI, that's Severe Weather Information. I'm also a member of Illinois Storm Chasers. For anybody who's not familiar with us, we are an online weather organization that provides forecasts across the state of Illinois. And I have a slide going a little bit more in detail about who we are at ISC. I study meteorology at Mississippi State University, and I've been storm chasing since 2015. One thing you guys will learn quickly is I am a complete weather fanatic, especially when it comes to severe weather. I know tonight I'm talking about winter weather, but severe weather is where I have all my chasing experiences, and that can be shared down the road as well. So in that time since storm chasing since 2015, I've documented 27 tornadoes across the country. But people always ask me, why did I get interested in weather? Why did I decide to do public speaking for weather, severe weather, winter weather, all the above? And for me, there's two main reasons. Number one, I'm sure every single one of us who are listening right now have either heard of or seen the movie Twister. Now, Twister was a movie I was obsessed with growing up. I mean, to the point when I would literally obsessively watch it. That movie came out in 1996. Now, I was born in 1994. So growing up, I was not supposed to be watching that movie. And my parents would tell me, Nicholas, you can't watch it. It's not age appropriate. Well, at that age, I did what every little kid does when their parents tell them not to do something. I went ahead and did it. So when normal kids were watching Cartoon Network, Nickelodeon, Disney Channel, I was watching Twister and the Weather Channel. So yes, I was one of those. I was one of those kids. A little bit different, but it turned into this passion I have today. But what I found is, even though I loved weather and loved the movie Twister, I found that every time weather would actually impact me, specifically severe weather, I was terrified. I mean, to the point when I would curl up in a ball and cry when there was a tornado warning for my house. And this lasted until probably the age of 10 or 11. And, I think back, like, why was I so scared of storms when they actually come near me, yet I love watching them on TV? And I stem it back to the 1990 Plainfield tornado, which, if any of you who are from the Northern Illinois region and were around here in 1990, you're aware of the Plainfield tornado. So you may be thinking like, well, Nick, you just said you were born in 1994. That tornado happened in 1990. Where's the correlation? That tornado impacted my family directly. My grandma's house was destroyed in Plainfield. My parents' house suffered damage as well. So hearing those stories growing up, I now thought that every single time the sky got dark, the next Plainfield tornado was going to happen. So it didn't go away until about the age of 10 or 11. At that point, I started learning more about weather and realizing just because the sky's dark doesn't mean a tornado is going to happen. Now it turned into this weird passion to see Mother Nature as close as humanly possible, and getting within a few hundred yards of tornadoes, documenting blizzards, everything you can imagine. So quite the about face for me. Now, a little bit about Illinois Storm Chasers. I mentioned that we're an online company that specializes in weather forecasting for the state. To this day, we have roughly 320,000 people that follow us, and we incorporated back in 2015. We also have a very close working partnership with the local National Weather Service as well as local media. Me, for example, I've helped the National Weather Service out of Chicago do damage surveys after tornadoes moved through the region. My last damage survey was the Woodridge and Naperville tornado from last year. Well, actually, sorry, it's 2023 now. So from 2 years ago now. And we also aid them in the warning process and some of our material the Weather Service is actually used for trainings as well. We also have 4-degree meteorologists on staff, and we also have a close working partnership with a tour company called Tornadic Expeditions. Now, what they are a company that takes regular people all across the country to chase weather, so specifically severe weather. So in the summer months, you can sign up for a tour, and you get one of us guides one of the members from Illinois Storm Chasers, as well as obviously the tour company. We take you out to see Mother Nature up close and personal. It's a great experience. Highly recommend it for anybody who ever wants to storm chase but doesn't quite know how to do it. So our staff starts with Danny and Adam. Danny, Neil, Adam, Lucio. They're the owners of Illinois Storm Chasers. Myself, my main priority is not only storm chasing, but this public speaking as well. Joe and Luke are our two main forecasters for our page. So if you're familiar with our Facebook page, you see forecasts posted on there. 99% of those forecasts are from one of those two. And then we also have Billy. He's our space weather expert down in far southwest Illinois, right outside of St. Louis. So now moving on to snow. So our average accumulated snowfall in our region ranges from about 2 to 3 feet on average per year. But one thing you'll notice as you go down south through the state, you get towards the St. Louis area, and they're only averaging anywhere between 6 to 18 inches of snow, depending on what size St. Louis you're on. So it's a pretty steady drop off across the state. One thing that's interesting, and I know we've all noticed it, is it seems like the past several years, winter has been pretty absent. At least snowfall has been pretty absent in the month of December, and even the first half of January. And this year is no real exception. This year we've barely had any snow. I know the northern suburbs have had a couple small events with a couple inches, but overall we've been very quiet in the snow department. But what I tell everybody is wait for that last week in January into the first week of February. It's pretty much a lock. Every year we get a significant storm system around that time period. But if you look up in the southwest Michigan area or western side of Michigan, you get into that lake effect snow belt, and your average snowfall, 72 to 84 inches. So a difference of 200 miles is a difference of, what is that? 24 to 72. So, several feet of snow difference within a 200-mile span of our local area. Just goes to show how influential, I can't say that word, Lake Michigan is in terms of increasing snowfall amounts. Now, if you're a snow lover living in LaSalle and you really, really want to see some snow, go to the lake effect snow belts in New York. Buffalo, New York, for example, this year is already over 100 inches on the season. So through all of December, already up to 100 inches. So what is that? 4 times our average annual snowfall in 1 month for Buffalo. So for those of us who don't like snow, LaSalle's a quite okay area. Now, when we look at the average number of 2-day snow totals for each month. So for 1 inch of snow in December, we'll start in December. On average, 4.5, so let's say 5 days per year in December, we have a 2-day snowfall total of 1 inch or more. And as you go up this list, you see how progressively smaller these numbers get, right? Especially, let's go into January and February. Snowfalls of greater than 6 inches over a 2-day span really only happen on average once, maybe twice every 2 years. So not as often as we tend to believe. I know it seems like every winter, almost every system that comes through, there's forecasts that are put out of like, oh, this is going to be a historic storm, or this is going to be a crippling snowstorm, so on and so forth, and then we get a couple inches of snow. As I said, climatology speaking, our area isn't prone to massive snowstorms. There's a reason why if we get a snowstorm greater than roughly 14 or 15 inches, we're already in the top, I think, 7 in history. But we do know when we get a big one, we can get a big one. It's just not all that often. When we look at the average number of 1-day snow totals greater than an inch, these markers, most in northern Illinois, as you see, are at that yellow marker. So between 8 to almost 13 days per year, we average 1 inch of snow. Okay. So, winter in our area tends to run from November through, unfortunately, April. It seems like we always seem to get some snow in April. So over that, what is that? Nearly 6-month period of being able to get snow, we only average 8 to 13 days with 1 inch or more of snow. Now, when we up that to 3 inches of snow per day, majority of the area, again, now we're talking 1.5 to 3.5 roughly days per year of 3 inches or more of snow. So again, like it just goes to show it's all in the numbers, all in the averages. Our snowfalls are typically of the moderate variety. And when I say moderate variety, I'm talking your 2 to 5, 3 to 6 inch snow events. Once you get 6+, it's exceedingly rare, or exceedingly, I shouldn't say rare, uncommon. When we look at this map, this is snow totals of 6 inches or more in a single day period. Talking about half a day to nearly 1.5 days per year on average. LaSalle, even 0.0 to a half, so about half a day a year. So once every 2 years to get 6 inches of snow in one 24-hour period. Now, that's not saying over a several day period of getting 6 inches of snow. This is just within 24 hours from midnight to midnight. Now, moving on to a little bit about model forecasting. I'm going to go much deeper into this later in the presentation. But general rule of thumb, with our mid and long range models, there's three major global models that we use to base our forecasting for the mid and long range. And when I say mid and long range, I'm saying anything past about 4 days. 4 days and on is going to be your mid to long, or even 3 days and beyond is mid range to long range. So the three global models that we really focus on is the ECMWF, which is the European model, the GFS, which is the American model, and the GEM, which is the Canadian model. There's so many more global models, but these are by far the most accurate. Not saying they're perfect, but out of everything, these are going to be the three that you want to look at more often than not. Now, these typically run at resolution between 9,000 and 12,000, or 9 and 12 kilometers, excuse me. What that means, it's giving you a coarse look at the atmosphere, the overall synoptic setup and pattern across the country, across the world. Now, this is not going to give you specific, down to the city level details, but as I said, it's going to give you an overarching theme of the weather pattern that's upcoming. Now, one thing you'll notice with mid and long range models, specifically once you get into the longer range, the reliability tends to go down substantially. So the GFS, for example, runs from right now out to 384 hours. The GEM and the European model run out 240 hours, so 10 days. As you get beyond about day 5, the reliability goes down exponentially. So when you have a model forecasting a system across the middle of the country at, let's say, hour 150, but in reality, that system doesn't exist, but the model thinks it does. Now, every hour after that point is going to be corrupted, and it's not going to give accurate information. The reason that's so important is, especially in winter weather forecasting, I'm sure all of us have seen, we watch the news, and some media outlets like to put up a 2-week snowfall total. And these snowfall totals are insane, 26 to 28 inches of snow across the Chicago metro area. And everybody starts panicking like, oh my God, we're getting 2 feet of snow. When in reality, they're taking that whole 384-hour period and putting that on a map to the general public, knowing that range, especially the second half of that range, which is where most of that snow is going to come from, is what we call fake snow. It's not going to happen just because that model run, once you get past that time period, just is not all that reliable. There have been times, however, where the models nail a storm system a week and a half out. The first Groundhog's Day blizzard was a great example of that. The European model picked up on that from all the way out from hour 240. And it did not change all the way through the event. Had one little hiccup 2 days prior to the event, but beyond that, it was incredibly consistent and it absolutely nailed it. Now, that is definitely the outlier. That does not typically happen, but once in a blue moon, these models can sniff something out in the extended range. Now, I'm gonna stop share real quick because I don't think I hit the audio button. So this video that I'm gonna play next, really good way to understand ensemble forecasting. So I'll give you a brief overview. Ensemble forecasting, essentially all it is it takes the global model and it will run that solution 50 times with a slightly different calculation, which will then give you a slightly different outcome. And those ensembles are important because it can give you more credibility to a model run. If all the ensembles are showing that specific outcome, then we have higher reliability in it, versus that ensemble comes back and all 50 ensembles are completely different, then we know confidence is very low. So this video does a very, very good job explaining it. This is going to be based off the European model, which the European model is statistically the best performing model that we have. So share sound, screen again. All right.
If we go back 25 years ago, we used to have one single forecast issued every day. Problem we had was that we didn't know whether the forecast was going to be accurate or not.
When we take observations of the atmosphere, it's like when you have a thermometer in a room, and if you put another thermometer next to it, you will not necessarily have the same reading because nothing is perfect, which means there's always uncertainty in what we measure and what we predict.
Ed Lorenz was one of the first to really cast it in a mathematical framework with which he was able to demonstrate that you make a tiny error at the initial time. That tiny error is going to grow into a very substantial error.
We always say that atmospheric weather prediction is an initial value problem. So we first determine what is the state of the atmosphere now, what is the initial value, the initial conditions, and then we run a model. Traditionally, people were just using one model typically in one center. They were just doing an analysis of the atmosphere, using one model, and then getting the forecast for the next few days. And that was very much what we were doing. We were taking the best image of the atmosphere with the observations, the best model we could get, and we had one shot in the future to say what the forecast is. Ensemble prediction is about running one model several times. And in particular here at ECMWF, we were trying to change the initial conditions of the forecast.
For each point over the globe, instead of having just one value of temperature, we have 50 value of temperature at the initial point. The same for wind, the same for pressure.
And this would actually trigger the atmosphere to go in different directions in our forecast.
Then I can estimate using all of them what's going to be the possible range of forecast. And this was, for example, extremely helpful in the summer 2003, when Europe experienced extreme hot temperatures. So with our ensemble system, we're able to predict these extremes 2-3 weeks ahead.
What we really use a lot is tropical cyclones and the trajectory of tropical cyclones. So there you look at it on a map, not on a given point, but you really look at the different trajectories of the tropical cyclones.
You probably have heard of Hurricane or Superstorm Sandy along the east coast of the United States, and that was a case where the ECMWF prediction system provided a heads up a day or two in advance of our own U.S. Weather Service prediction systems, and that was a success story.
So I think at the beginning we were trying to really push the forecast where it was going to be sensitive. Then we started also to incorporate some idea on the uncertainty in the observations, sort of quantifying actually what comes from the uncertainty in the observations themselves. And finally, the third step has been to actually quantify what is the uncertainty in the model itself. We know there are some ranges where some parameters could lie, for instance, and so it's quantifying these as well.
So now if I think about the future, we want to make our models better. We know, for example, that the coupling the models to the ocean is key, and we have started doing that. We want to improve the initialization of a model to our estimation of the state of the atmosphere. Third big area of work is resolution. So we need more resolution in the system.
We have a very high collaboration goal that we really think we benefit if we collaborate with other organizations.
Oh, my colleagues and I really think the world of ECMWF. The scientists are really defining the forefront of the operational ensemble predictions and where the research needs to head to address the remaining deficiencies in ensemble prediction systems.
Yeah, it's fantastic, extremely motivating to know that you're working in a place where you can really make a difference. And whenever we have a good success in our forecast and we think we might have saved lives using the science to do that, I can't think of anything better to do.
All right. Go forward. Oh, there we go. All right. So one thing I'll point out too, which watch that video, it reminded me. Number one, the European model is increasing from 50 ensembles to now 100 ensembles. So we'll see how that goes. But one thing that we've also noticed with the reliability of our models is it almost seems like to a lot of us that model reliability has actually gone down over the past several years. That models have actually gotten worse with the improving technology. One reason I believe that's potentially the case is our models, our global models, our longer range models have become higher resolution. So now they're picking up on things on a more mesoscale, on a smaller scale. And that negative feedback, if it's bad info, is now corrupting the model runs sooner. Hence why there's the blizzard that was predicted a few weeks ago, the Christmas blizzard, that didn't really pan out. I will say, even from our perspective, we were pretty confident on a high impact, potentially historic blizzard, even out to about 84 hours out, 72 to 84 hours out. And then the models, just all the models at one time, completely flipped. And, you know, thankfully with us at ISC, we ran very conservative with our totals initially, and we never had to raise them, but never had to lower them either. There were, even though internally we were like, this is gearing up to be a big deal, and it still was. I mean, we still got a couple inches of snow coupled with the extreme cold and the extreme wind, so it still made a high impact event, but nothing near what potentially could have been. I know even out 3 days, which is when we normally get into our zone of like, okay, you know, we're starting to feel a little bit more confident about snowfall totals. Even 3 days out, the models were still pushing 1.5 feet. So that's why it is kind of a humbling storm, because it all switched and took a 180 at the last minute. So a little bit about short range models. Short range models is what I talk about usually inside of 84 hours. We call them convective allowing models. So they basically allow, the models are allowing or showing convection, so thunderstorms or convective winter weather. Main models I use are the HRRR, the NAM 3 kilometer, the NAM 12 kilometer, and the rapid precision or the RAP. These typically run at a much finer scale of 1 to 3 kilometers, meaning you get much more mesoscale features, or many more mesoscale features in individual storms, individual snow bands, mesoscale banding, all that stuff when it comes to weather. They update very frequently. The HRRR is every hour. The rest of those models update every 6 hours. So the other ones, we get 4 runs of those a day. And their forecast intervals are every 3 hours versus the globals, which are every 6 to 12 hours, in terms of, you know, going from hour 6 to hour 12 to hour 18 versus the short range, which go 3 to 6 to 9 to 12 to 15 to 18, so on and so forth. Now, when we look at the different sorts of events we see in the wintertime, obviously we have our rain-only events, our salt washers, as I like to call them. So essentially, when in the wintertime, when we have a rain-only event, there's no surface temperatures near or below freezing. Pretty self-explanatory there. Lift, moisture, and instability, which are three of the 4 ingredients for severe weather, are considered for the forecast of just rain. Models typically do a pretty good job with the QPF, which is quantitative precipitation forecast, essentially how much precipitation is going to accumulate. And they typically do a pretty good job with that overall. Sometimes they trend a little bit downward as the system nears. That's common. They go from, let's say, showing in this case, 3 inches over in Iowa. As we get closer, that may dwindle down to 2.5 inches. Still a significant rainfall event, but not quite significant as it potentially would have been. Now, when the temperatures are below freezing, of course, we get into our snow events. So when freezing rain and sleet have been completely ruled out, we know that's not going to be a precipitation type, and we know it's going to be all snow. There's additional things that we have to look out for. Number one is snow ratio. Basically, all the snow ratio is if you melt down the snow, how much liquid do you have? Okay, so that's number one. Number two is lift. You need to know where the lift is strongest within the cloud and whether or not the deep moisture that accompanies that system coincides with that area of strongest lift, because that's going to help aid in increasing your snow ratios to give you more snow. And then the last thing that we have to consider is the type of snow crystals. Depending on the temperature and the moisture content through the atmosphere, it will affect how the crystals form, how they fall to the earth, how they stack, how they accumulate, all that stuff. When we talk about snow ratio, our typical snow ratio is a 10-to-1 ratio, which all that means is 10 inches of snow equals 1 inch of liquid. That's what you're going to hear on TV a lot. average snow liquid ratio 10-1. Okay. That is typically wrong. So our snow ratio throughout the duration of event is never the whole event 10-1. It might start as, let's say, 8-1 snow. And then as the system is departing in the last few hours, maybe it's up to 18-1 ratio snow. So saying 10-1 throughout the entire event isn't always all that accurate, and that's where you can get some really inflated snowfall totals. Realistically, they can be as low as 3-1. 3 inches of snow equals 1 inch of liquid. Absolute cement snow, gross, nasty, pain in the butt to clear, not fun. And it can be as high as 100-1. We have never seen 100-1 ratio snow in our area, but you get out to the Sierras, on the Rocky Mountains, you can get snow ratios that get into that area. And that's your incredibly light, fluffy snow. With 100-1 ratio, you would sneeze and you'd probably blow away 6 inches of snow. Now, snow ratio, it's just basically how heavy the snow is. 8-1 and lower is your really heavy, wet, heart attack snow. 11-1 to 13-1 is your average for our region. And then 20-1 and up is your very light snow. You can sweep it off with a broom, don't even have to bring out the shovel. Also very highly susceptible to blowing and drifting. Now, when we look at the Diedrich growth zone, have me say that 10 times fast. It's essentially the zone in the atmosphere where the snowflakes are made. So it's typically between -10 degrees Celsius and -20 degrees Celsius. Ideally, perfect world, -12 to -18 is your zone. But we'll go with -10 to -20 degrees below Celsius through the atmosphere. So where the moisture content lines up with the temperature within that zone, that's going to determine your flake size. So when we get dendrites, these are your big fluffy snowflakes. Your snow ratio is typically in that, can be as high as 25-1. Now, when there's not as much moisture content within that zone of -10, -20 through the atmosphere, now you start getting smaller snowflakes. These still stack efficiently and still accumulate efficiently. But then as you fall below into drier air, you get all these, we call them plates and columns and needles and prisms. These are your inefficient snowfall accumulators. These are the ones where it can snow for hours on end and you end up with an inch of snow. You need your big dendrites to get those really high snow accumulations. Blah, 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 blah. So the reason why the dendrites are so efficient at stacking up and accumulating to higher totals is because as they fall, they're very light and fluffy, and you get air pockets in that snow, which allows it to stack quicker. Versus if you have solid plates where the pretty flat, surface area is flat and everything just stacks on top of it, and it compresses and doesn't stack efficiently. Now, this you may look at and be like, what the heck am I looking at? Okay, so I'm going to walk it through with you. Remember when we said for the DGZ, I'm not going to try to say the growth zone because I can't. So the DGZ, so -10 to -20. So when we go vertical in the profile, that's us going higher up into the atmosphere. The temp profile runs on this diagonal line. So this dark blue is your DGZ, okay, between -10, -20. When you have the temperature profile, so the red line is your temperature, okay? Your green line is your dew point, the measure of moisture in the atmosphere. When these are real close together or touching, you're saturated, which means there's going to be precipitation falling through that column of air. So when we look at -20 up here going all the way up and -10 down here, we see that we're nearly saturated all through this growth zone. So okay, like that's a good snow sounding. We're like, okay, we know there's going to be snowfall. Now it's just determining what are the flake size, what kind of flakes are we going to have. And quick reference, this pink line is your 0 degrees Celsius, 32 degree freezing line. So obviously this sounding, we're well below freezing all the way through the column. We have no chance of mixing. We know this is going to be 100% snow. So DGZ, again, we're going to go -10, -20. Technically, it could be -12 to -18. So when we go one more, when we look at this right-hand image, UVV, it's upward vertical velocity. So it's how fast that air is rising through the atmosphere. So when this bends to the left, you know you have really strong vertical velocity. And when that lines up with, goes through this zone, this DGZ, -10, -20, and it coincides with an area of saturation, the temperature and dew point touching or very nearly touching, now we know we're going to have very efficient snowfall production. We're going to have the big deaderites. We're going to have snowfall ratios that are going to be inflated versus what they typically would be outside of this zone. So when we see this sounding as a meteorologist, we're like, okay, we know this area, wherever the sounding was pulled, is going to have a high likelihood of some significant hourly snowfall rates. Now, going back to rain, if the majority, and we're going to look at the skew-T plot again. So 0 degrees Celsius, 32 degrees Fahrenheit, our point of freezing, right? To the right of that's above freezing, to the left of that is below freezing. So if the majority of the lowest 5,000 feet is above freezing and above 3 degrees Celsius, which is dotted lines 3 degrees Celsius, the precipitation will be rain. Even if there's another near surface cool layer, so if we go back below zero a little bit or towards zero, it's still going to be rain. Reason being is once you get to 3 degrees Celsius, that snowflake that started up here is now completely melted. So no matter what, you can never get that snowflake back. Okay, even if that surface temperatures might marginally supportive of snowfall. So when we look at the column, snowflake starting up here, right? As you come down towards the surface, still snowflake, you hit 0 degrees, 32 degrees Fahrenheit. Now the melting process starts. At this point, right between 0 and 3, you have a partially melted snowflake. Now you cross this 3 degrees Celsius threshold, now you're completely melted. As you come down towards the surface more, it's like, oh, we got below freezing again. And then it's like, okay, so that could potentially raise a concern for some freezing rain, which we'll go through in a little bit. Now, as you come down more towards the surface, we cross this 32 degree, 0 degrees Celsius line, and we're above freezing at the surface. Therefore, we have the rain. And this will all make sense once I go through the rain, sleet, snow, and freezing rain. Now, snow, when your whole column is below freezing, even if there's a little bit of a warm layer that sneaks in the mid levels and partially melts that snowflake, as long as it's not in that area of above 0 degrees Celsius for that long of a time, you're still going to have a chance at a snowflake at the surface. So again, starting up at the cloud bearing layer, temperature is well below freezing. Come down towards the surface, you have a slight period where it gets above, but not enough to quite melt that snowflake. And then we quickly go back to well below freezing all the way down to the surface. So once again, you're going to be snow through the whole column, as long as we stay for the majority of the time below 0 degrees Celsius or 32 degrees Fahrenheit. Now, when we look at sleet, sleet can get very complicated, okay? So sleet, you essentially have your initial snowflake in the cloud-bearing layer, and you bump above 0 degrees Celsius, but don't quite reach that 3 degrees, but come real close, and then slowly fall back towards freezing, and then go solidly below freezing at the surface. What that's going to do, your snowflake up here, it's going to get to above freezing. It's going to partially melt, but that water droplet's still going to be basically what we call supercooled, so still at or below freezing. So as it falls back through the layer and gets solidly cold again, that quick jump to well below freezing, now that water droplet's going to turn into freeze and turn into ice, and that's when you get your sleet pellets at the surface. Sleet does not happen all that often for an extended period of time. There's been a few documented sleet storms that we've had over the past 10 years, but to get environmental conditions that favor sleet for hours on end is pretty rare, really anywhere in the world, and here's no exception. We will get sleet occasionally as precipitation is changing from rain to snow, or even snow to rain. We occasionally get that transition period of sleet. And then the other precipitation type, freezing rain. So freezing rain, similar to rain, main difference is the surface temperature is well below freezing. So snowflake up in the cloud bearing layer again, come down the column, and you get well above freezing and well above even the 3 degree Celsius. But it's at a level of the atmosphere where you'll get complete melting, but that water will still be super cooled. So now you come back down again, dip below freezing and below freezing at the surface, and you get your freezing rain. So freezing rain, obviously as it's falling, it looks just like regular rain. That's why it can be the most dangerous. Roads ice up quickly. If anything, when freezing rain occurs, anything that is below freezing, whether it be the roads, whether it be your car, whether it be trees, anything, it will instantly freeze on there, cause some heavy weight to the power lines, trees, cause some damage, and then of course make the roads an absolute mess. Now, when we talk about wind chill, so wind chill, it's essentially what the air feels like to your skin. So you can, a few weeks ago with the Christmas storm, when we had those negative 40-degree wind chills, actual air temperature was, I believe, -8, -10. Some areas bottomed out to the negative teens, but our wind chills were well below -40. So that's what it feels like on our skin. But the thing is, with wind chills, inanimate objects don't feel wind chills. They just feel actual air temperature. So when you think about your pipes freezing in your house, and it's like the wind chill is -50, like my pipes are going to freeze. Well, they may, but it's going to be the cause of the air temperature. So let's say the air temperature is -20. It's not going to be based off the wind chill. The lowest recorded wind chill in Chicago ever is -82 degrees. Now, they redid the wind chill criteria back in the early 2000s, and that -82 actually equates to -55 on the new scale. So this year when we had wind chills in the -40s, and then back in 2019 when we had wind chills in the -50s, we were on par with that all-time record. So on the right-hand side, when you look at the wind chill map, it's just the frostbite times are color-coded. So as you get colder and the winds increase, your wind chills get more and more substantial. So you can get below 0 wind chills with temperatures still well above 0. 20 degrees, you get 60-mile-an-hour winds, which I don't know how likely that is, but you can technically get below 0 wind chills with temperatures still in the upper teens to low 20s. Now, once you get around air temperature 0 degrees Fahrenheit, even the slightest wind is going to have a huge impact on wind chills, going all the way down to the exceptionally dangerous category where you get frostbites in 5 minutes or less. Now, talk about frostbite. So there's 4 degrees of frostbite. First one, most of us have probably had it at one point or another in our life. It's 1st-degree frostbite, where your surface of your skin frozen. It's otherwise called as frost nip. Your fingers are really red. You touch them, they're kind of hard to the touch. Don't really have much feeling in them. And then you get into a warm area and you warm up and everything's fine. 2nd degree, this is when your skin, deeper layers may start to freeze and harden, and that's when you get blisters, similar to just a burn from something hot. Frostbite is very similar in that sense, just the opposite. So blisters form in a day or two with 2nd degree frostbite. 3rd degree frostbite, that's when you get into much more serious and substantial injuries. That's when your muscles, tendons, nerves, and blood vessels freeze, and you may have permanent damage to that affected area. And then 4th degree, it's what you see on the news when people get stranded. That's when your skin gets dark blue or black. Gangrene is a real threat at that point, which would require amputation. I hope that none of us have ever experienced that. I know myself, I have not experienced that. I do not wish to experience that. But that does happen when people are not prepared or get stranded out in the elements. Now, some wind chill and cold myths that are common. Number one, that you do not need sunscreen in winter. So this is one that, for our purposes, you probably don't. But if you like to go skiing, if you ever have been to the Rockies, and skiing in the wintertime, you will get sunburned on the slopes because the sunlight reflects off the snow and back into your face. And at that point, during the winter, the sun is actually at its closest point to the earth than any point throughout the rest of the year. So the radiation exposure is actually higher in the wintertime than it is in the summertime. Reason why we don't really burn too bad in the wintertime, at least if we're just walking around outside, is because the sun angle is lower. So less time with the most powerful rays, but we still deal with all the radiation. Number two, that the body loses most of its heat through the head. It's something that honestly I believed until I started researching winter weather. So our head loses no more heat than any other part of our body. If your head accounts for, let's say, 7% of your body, then your head will give up 7% of your heat. If you expose 7% of another part of your body, that part of your body will also give away 7%. So it's proportionate to anywhere on your body. Obviously, if your head's completely exposed, it's going to take up a larger percentage. Therefore, you may feel colder. Number three is cold air will give you a cold. That is not true. You can have, essentially, the cold air itself does not directly increase your chance of contracting a cold. The winter time, a lot of us are stuck inside, especially if we work and we're in an office with other people. That's when we can run into, you get those viruses and those bacterial infections, and then you're out in the cold, and then you get sick, and then you're like, oh, the cold got me sick, when in reality, no, it's just because we're around more people in a closed setting where the air isn't filtered and you're not getting fresh air. So the cold has nothing to do with actually receiving a cold. It's just the fact that we're usually around more people in the colder months. So what does all this mean? So at the end of the day, kind of going back to snow and snow ratios and precipitation types, variations of just a few degrees can completely change the forecast. In the summertime, we may have 75 degrees outside. Well, if that high only reaches 72, nobody really bats an eye. And the precipitation type at that temperature, no matter what, is going to be rain. But in the wintertime, if we're forecasting an air temperature of 31 degrees and snow, and we get an air temperature of 34 degrees, that can completely change our forecast. And now we get all rain or a mix of rain and snow and severely cut into our snowfall totals, and vice versa. Sometimes when it's colder than forecast, we can get a little bit more snow than what was anticipated. Wet bulb temperatures below 32 degrees, which is essentially the point at which the air is saturated, can result in this snow, sleet, wapple, despite actual surface temperatures above freezing. So that's why sometimes in the month of April, let's say, temperatures like 38 degrees outside and you have snow pellets and sleet pellets falling from the sky. Has to do with a cold layer near the surface, slightly, basically from the mid-levels to near surface, that can partially refreeze that precipitation. All right, so now I'm gonna get out of this presentation. I'm gonna look over some models now. So this is kind of what I wanted to show you, and hopefully, let me see if I can move this box. Oh, I can, sweet. Sorry, I got very excited there for a second. All right, so I have a pen, so I'll be able to draw on here too. But when we talk about the global forecast system, the GFS, okay? So I mentioned we have a storm coming in, a storm system on Thursday. So let me go back. So when we always talk about how storms emerge from the Rockies, that's going to determine, the impact downstream, whether it be us or up the East Coast. Okay, so when we look at right now, California is being, absolutely just hit hard with significant rain, flooding, high winds, heavy snow in the mountains. Now, this piece of energy, this storm system is entering the West Coast right now. Now, as I move forward in time, 9 hours out, 18 or 12, 15, 18. So now we see this area of closed off isobars, which is lines of equal pressure. So now we know we have a closed off circulation. This is going to be what we call our low pressure system. So let's see if I can draw on here, line, make that red. So our low pressure system. Low pressure systems, I forgot I can draw on my screen. It'll actually make it a lot neater. So our low pressure system accounts for all of our weather on Earth. High pressure dominates calm weather, low pressure, stormy weather. So we have our low pressure system out here right on just past the Rocky Mountains in eastern Colorado. Now, what happens next is going to determine what our potential impacts are downstream. So let me get rid of this real quick. Get rid of that. So as we go further down, now we see this low pressure system developing more. A little bit of snow on the northwest side, rain down on the southeast side of that low pressure system. Now, let me go to 500 millibars real quick before we look at precipitation. I want to look at one other thing first. So this is what we call vorticity. It's essentially the atmosphere picking up like where there's rising motion in the atmosphere to potentially create a storm system. So there's gonna be two areas. We have area A. So let me do a color that you will actually be able to see on this map. Let's do blue. Okay. So area A is gonna be this area right here. Okay. And then area B is gonna be up here. What that is, this is our southern stream, and this is gonna be our northern stream. To get high impact winter weather in our area, you need these to phase. You need that southern stream and northern stream to phase and come together. When that doesn't happen, a lot of times the southern stream will kind of get strung out and head more west to east and won't be as strong. But when these two combine, the southern stream and northern stream combine, the energy ramps up, it gets stronger, and then it'll start curving to the north. And on the northwest side, so this area over here is where you get your heavy snow, rain over here, and then severe weather usually trailing down to the south. So what's going to happen with this storm system, move that box out of the way. As you go forward in time, just watch this area up here, this northern stream and the southern stream, and you'll see if they come together. Nothing yet, nothing yet. Still really nothing. And now it's starting, this northern stream is starting to wrap around into the southern stream. So now it's starting to phase. But the problem is, this low pressure system is already over northern Indiana and past us. So as we go forward in time, that northern stream wraps all the way in, southern stream wraps up and into the northern stream, phases, and continues on. Now, when we look at the winter precipitation type, we'll see, going back in time, as it comes near us, it kind of skirts to our south. It's primarily rain on the northwest side, which is not all that common for this time of year. Normally up here, it would still be snow. We have our closed off low pressure system, but it doesn't really look all that great. But this is when the phase is starting to occur. This is when that northern stream right here, southern stream through here are starting to wrap up and combine into each other. So you're going to see, as I go forward in time, now the system starts wrapping up. Now you start getting heavy snow on the northwest side as you get into Canada, heavy rain on the eastern side, and it turns into a pretty sizable snowstorm. If I go to snowfall accumulations, total snowfall, you can see as we get into Canada, the totals are, 9 to 10, 12, 14 inches because it phased at that point. If that phase was to occur further west, get rid of that box. If this northern stream and southern stream phased earlier, let's say they phased right there, that storm system would actually track further northwest, be stronger, and also pull in a lot more cold Canadian air. So when I look at the surface, when I look at temperatures, another good representation. So again, closed isobars, center low pressure, ejects from the Rockies, goes into the southern plains, starts wrapping up. And you see these temperatures across northern Illinois in the upper 30s, normally where there'd be snow, because this northern stream bottles up all that cold air. And since it never phased, there's nothing to be able to pull that cold air into the system. So all we have is warm, moist air riding up from the Gulf of Mexico into the system and giving us these mild temperatures for January standards. And then as that system phases right about here, you'll see now we get that cold air wrapping in. So now we have temperatures right around freeze, upper 20s to right around freezing in that area of snow. So now that cold air is coming around the back end and feeding back into the low pressure system, thus giving you the heavy snow and the higher snowfall accumulations. So I like to show that just because there's so much working in the atmosphere. Even one other thing I'll show, I'm sure we've all heard of the jet stream. Okay, I'm actually going to zoom out on this. I'm going to do North America as a whole. So here we are right about here. Go back in time. So the jet stream. So along the jet stream, what you get is you get ridges and you get troughs. So ridges go up, troughs go down. On those ridges and troughs, on the ridge, you get area of high pressure. So relatively, I keep forgetting I can draw on this. I'm giving me much cleaner lines. So let me redo that because that is not legible. That's what I get for trying to draw that out with my mouse. So on the ridge, you get area of high pressure associated with sinking motion, calm weather at the surface. And then at the base, especially the right exit of this jet stream coming down, going through the trough, and on the right-hand side, that's where we're going to get our, let me click out of that. Oops. That's where we're going to get our area of low pressure, our stormy weather. So just whenever you see a jet stream, you see that ridge going up, as you know, below that, you're going to have tranquil weather. And then where that low pressure system is, especially on the right exit of that jet stream, you always hear Tom Skilling. If you watch WGN, you hear Tom Skilling be like, we're on the right exit region of this 120 mile an hour speed max. And this is driving the weather. You'll hear him say that all the time. And this is essentially what it is. On the right-hand side of this emerging jet stream coming off the trough, that's where you get your maximum area lift and precipitation and storm system to wrap up. So even if I stepped it out even further and get rid of the pen, step it out even further to the world, you're going to see how the jet stream goes all across the world. So as we go through time, we eventually get this weather that's off of Japan's coast. And it just travels, everything's fluid. The atmosphere is incredibly fluid. You know, our air is just like liquid, just like water. So with that being said, I see we're at 6:58. So I'm going to go ahead and wrap it up on my end. I don't know if there's any questions in the chat box. I can't see the chat box, but we can definitely answer your questions. If you have any questions, feel free to post them in there. I'd love to answer them. But yeah, I will go ahead and turn it back over to Donna to see if there's any questions.
Quite the lesson in weather, Nick. Thank you. I don't see anything in the chat box right now. However, let's go way back to the beginning because I have a question. So since this is all in our heads that we're suffering through such horrific winter weather and snowfall when it's really not that common to have deep snow, is it the wind that makes such a small snowfall seem so much worse? The combination of drifting and then the wind chills? Is that why we all have this preoccupation with winter here? Yeah,
I mean, yes. So especially out in your area where you're very susceptible to blowing and drifting, that's absolutely, you know, a factor that makes our winter seem even more brutal. I will say in terms of average snow, I mean, we still average anywhere from 24 to 36 inches, depending on the area. Even some areas closer to Lake Michigan in the northern suburbs can get up around, you know, 36, 37 inches. So, I mean, we still do see our fair share of snow. But we usually have, you know, one or two of our quote unquote moderate to larger snow systems. And then we get peppered with a lot of, like, you know, 2-inch events, 3-inch events, things of that nature. So, yeah, the blowing and drifting and the wind chills definitely gives us that quote unquote Chicago winter.
Yeah, that sure is. So tell me, why is the European model the best performing for weather? Is it just winter weather, or did they have the best performing model in general for severe summer weather too?
So they're best performing all year round. Statistically, they're the best performing. Reason being, quite honestly, the European model, people at the forecast center they've invested the necessary money and research into it, versus the American model, where it tends to struggle a lot more. We haven't put as much of a focus on really developing it and fixing the issues with it. They come out with upgrades, quote unquote upgrades, and they actually sometimes make it worse. So it's, for whatever reason, the people over at the ECMWF, they have that secret sauce, and they're just doing really well with it.
So when we're talking about the American model, are we talking about NOAA? Are we talking about National Weather Service? Are they the same thing?
Yeah, so NOAA is the overarching, like they're basically the big guy, and the National Weather Service is off of them, and then so on and so forth. So when I talk about the American model, it's the GFS model, which is NOAA implemented it, and the National Weather Service aids in the upgrades of it and the maintaining it and whatnot. But yes, it's all a part of NOAA.
We do quite a bit of programming in conjunction with NASA, both looking out into space and programs regarding the satellites that are Earth facing. And I know there are a lot of, GPM, the global precipitation measure, and a lot of things that look inward. And so is it just we're not putting the commitment financially behind the technology? Is that what's going on, in your opinion?
Yeah, I'd say that's definitely part of it. When we talk about models, when the models run, it's a countless number of supercomputers doing quadrillions of equations in an incredibly small amount of time. And as I said, unfortunately I don't know all like the nitty-gritty details of the why behind, just because of the people much smarter than me run that stuff and are more fine-tuned to it. But what I can say is from kind of my perspective, it just seems like the European model, the people at the ECMWF just really put more effort into it. Not saying that we're not trying, but I think they have something that's working, and of course they're technically, indirectly a competitor, so they're not going to be like, hey, let's leak this information.
They're keeping the secret sauce.
Yeah, they have something over there they're doing that is their models verify better than ours.
And I imagine that since they're already on the hunt on this, they probably are tweaking it ever more every time, right?
Oh, absolutely. Yeah, that's what I said earlier. They're coming out with, I think this year they're going to increase their ensemble runs from 50 to 100 ensemble members. So I'm happy because we get their data to use it. So,
Sure.
At the end of the day, it's any of these models, if they can get better, we're all for it, because it just increases the reliability and the potential forecast skill.
Yeah, and potentially safety.
Absolutely.
So then when we're watching all the hurricane predictions, in the Gulf or off the coast of Florida into the Atlantic, I suppose we should be focusing on that European model.
Yeah, and I will say our model, it does have its wins. There's times when the GFS beats out the European model, and vice versa. So that's what makes forecasting so difficult, because you can have the European model, let's say, nail 2 or 3 events in a row, and you start putting more stock into it. And then it completely burns you because it's completely wrong. So that's what makes forecasting so difficult. And that's why, we tell people, yes, the European model is the best performing model, but you never want to put all your eggs in the European basket. You want to look over all the models, see what all the models are showing, see what similarities all the models have, and start taking kind of a consensus approach.
Makes sense. Well, I see that I'll probably get more questions tomorrow, Nick, and I'll pass them on to you. We are recording this program, and we will be posting it tomorrow. So if you do have more questions for Nick, please forward them to the library, and we'll make sure that we contact him and try to get some answers for you. Also, I wanted to mention that on March 21st, Nick will be back with us to discuss severe weather, all of our spring tornado issues and those hot, sultry days in July and August. So we will look forward to that. And I was taking an interest in your storm chasing opportunities that you have for people. So if you do that, Nick, with any of our library patrons and they go storm chasing with you, we're going to do a program on that too. So make sure everybody fastens their seatbelts. I think that we do have a comment up here. How much is your snow potential affected by what is going on in California, Nick?
So you're saying just like in general, like with, droughts and high precipitation rates out there, like how it downstream, how it affects us, I'm assuming?
Yes, I imagine.
Okay, so it has a big effect. Big droughts out west in California, Colorado, and all those states. It has an effect in our moisture return if our moisture source for that system is from the Pacific area. So if our moisture feed for a storm system, which does happen, comes from the Pacific instead of the Gulf of Mexico, and it goes over that real dry land, you lose some of that moisture content, which therefore will then decrease our precipitation or snowfall in our area. So not hugely common in the wintertime to have a huge effect because most of our source region for our moisture in the wintertime is from the Gulf of Mexico. But in the summertime, droughts out west do have a pretty substantial effect on our severe weather.
Okay. And we'll cover more of that in our spring program. Nick, regarding California, of course, there's been such devastation there and the mudslides. But they've been so, desperately in need of water. Surely this is, filling reservoirs and filling rivers, but is so much of it being lost because of the mudslides and the runoff? I mean, is this helping California at all?
So it is helping, but to your point, there is a bunch of runoff, so a lot of it is going to waste. When you're in a drought, you never want to have these extreme rain events because it does open up especially out there, opens up the chance of the mudslides and all those other, issues that arise from flooding. But yeah, I mean, it's to have that kind of rain. Yes, technically it eliminates that drought, but it causes a bunch of other issues. So you'd much rather have, just a steady period of moderate rain where the ground can soak it up sufficiently, the reservoirs get filled up properly, without all that added damage and devastation.
Yeah. Well, all eyes on California, and we'll be looking forward to the end of January and the beginning of February to see how we do, Nick. I think that's it for right now. We will see you back on the 21st, but for tonight, I want to thank our audience for attending, and I hope that everyone has enjoyed the program as much as I have. Please be reminded to complete the short pop-up survey that will appear when we close the Zoom connection. And with that, Nick, I'll turn it back over to you for closing comments.
Yeah, so thank you everybody for listening in tonight. I truly appreciate it. I hope you're able to take something away from this. As I said, in March, I'll be back to talk more about severe weather as we approach our severe weather season. But I truly thank you guys for tuning in tonight. stay safe. And if you guys tune in for the March program and we do not get a snowstorm that last week of January into the first week of February, I give everybody permission to yell at me because I was wrong. So with that, thank you so much and have a great rest of your night.
Thank you, Nick. And thank you to our audience. Until next time, good night.